All right, welcome. Today we're doing something, well, pretty incredible. We're going to build an AI that can literally help doctors diagnose disease just by looking at a picture of your retina. We're going from pixels to a real prognosis, and we're doing it all from the source code. So let's just dive right in.
And this really is the big question, isn't it? Can an AI actually learn to see the world like a doctor does? I know, it sounds a little bit like sci-fi, but that's exactly what we're here to do. We're going to build the AI that answers this, and we're going to do it together, step by step, right from line one.
So here's the game plan. First, we'll nail down the mission. Then we'll set up our digital lab. After that, we'll get our hands on the patient data, which is super important. Then the fun part, training our AI doctor. We'll give it a final exam, and to top it all off, we'll actually get to see the world through its eyes. It's going to be quite a journey.
Okay, Section 1, Pixels to Prognosis. So, what's the mission here? Simply put, we want to build a tool that can look at a retinal scan, the kind you get at the eye doctor's office, and spot the signs of diabetic retinopathy. This is a huge deal because it's a leading cause of blindness. So this isn't just some cool coding project. We're talking about technology that could have a massive real-world impact.
All right, let's get into Section 2. Before we can get to all the cool AI prediction stuff, we've got to do the prep work. You can't just jump into an experiment. Every good scientist has to set up their lab first. Ours is a digital lab, of course. But believe me, getting this foundation right, it's absolutely crucial. Everything else depends on it.
So first things first, reproducibility. We set something called a seed to the number 42. Now, why do we do that? Well, AI training has a lot of randomness built into it. This seed is like a bookmark for that randomness. It makes sure that every single time we run this experiment, all the random decisions are identical. It means our results aren't just some lucky fluke, they're scientific and repeatable.
Next up, we have to tweak what are called hyperparameters. The best way to think about these is like the dials and knobs on a complex machine. We're setting the image size, the batch size, which is just how many images the AI looks at in one go, how many full training cycles or epochs it'll run through, and the learning rate, which is kind of like how big of a step it takes with each new piece of information. None of this is random. Each one of these settings is a careful choice to make sure our AI learns in the best way possible.
Okay, lab's all set up. Now for the most critical asset of all, the patient data. I can't stress this enough. In AI, nothing matters more than the data. You've probably heard the saying, garbage in, garbage out. Well, it's absolutely true. An AI is only as good as what it learns from, which makes prepping these patient scans probably the single most important thing we're going to do.
And right out of the gate, we've got a major problem. Take a look at this chart. This is a classic issue with medical data. See that huge bar? That's all the healthy retinas. And then you see these tiny little bars for the different stages of the disease? This is called an imbalanced data set. If we're not super careful here, our AI will just get lazy. It'll learn to guess no disease every time because, hey, that's usually the right answer. And that would make it completely useless.
So how do we fix that? The solution is actually pretty clever. It's a technique called class weights. In simple terms, we're telling the model, listen, I want you to pay way more attention to these rare disease cases. In fact, if you get one of those wrong, the penalty is going to be huge. It's like putting a weighted grading system on its test. This forces it to focus on what's important, not just what's common.
Okay, data is prepped, it's balanced. Now it's time for the main event. This is it. Welcome to the AI's medical school. We are about to put this thing through its paces and turn it from a general-purpose model into a highly trained medical specialist.
Now, we're not exactly starting from zero. We're standing on the shoulders of giants by using a model called ResNet 50. Just think of it like this. We've hired a brilliant PhD student who's already an expert at recognizing patterns in any image. Our job isn't to teach them how to see from scratch, no way. Our job is to give them a super specialized fellowship in retinal disease. We're fine-tuning their existing genius. This whole idea is called transfer learning, and it is a total game changer.
And we're not just going to train it once and call it a day. That's not good enough. We're using what's basically the gold standard for training, 5-fold cross-validation. Here's how it works. We chop up our data into 5 equal chunks. We train the AI on 4 of them and give it a test on the one that's left over. Then we do it again and again, 5 times in total, each time using a different chunk as the test. It's like making the AI take 5 different final exams. This way, we know for sure that it's actually learned the material and isn't just, memorizing the answers.
So, after all that, this grueling exam process, what's the final grade? we get a mean accuracy of 91.87%. Now remember, that's not just from one test. That's the average score across all 5 of those tough exams. A number like that gives us a ton of confidence. It tells us our AI isn't just guessing. It has genuinely learned to see the patterns of this disease.
Okay, so our AI has graduated, you could say with honors. But training is one thing. Now it's time for the real world. This is like its final board certification exam. We're about to unleash it on a fresh set of patient images that it has never, ever laid eyes on before. This is where we find out how it will really perform when it counts.
And here it is. This table is basically the AI's final report card. It's called a confusion matrix. See that nice line of numbers going down the diagonal? That's the good stuff. That's every time the AI nailed the diagnosis perfectly. But the numbers off the diagonal, that's where things get interesting. That's where it got a little confused. We can see, for example, exactly how many times it thought a mild case was actually a moderate one. This gives us so much more information than just a single percentage.
So what's the diagnosis for our AI? Well, it's fantastic at telling the difference between a healthy retina and a diseased one. And it's also really good at spotting the most severe cases. Where does it struggle? Mostly in the shades of gray, telling the difference between, say, mild and moderate stages. But honestly, even human experts can struggle with that. The bottom line here is that its potential as a diagnostic tool is, well, it's incredibly strong.
Look, getting a 91% accuracy score is great, fantastic even. But in medicine, what the answer is isn't enough. You have to know why. You need to show your work. So for this last part, we're going to pop the hood on this AI and actually see how it's thinking. Trust me, this is where it gets really, really cool.
The magic trick we use for this is called GradCam. I know, it's a mouthful, but forget the name, just focus on what it does because it's brilliant. It creates a visual heat map, kind of like a weather map, right on top of the original image. And this map shows us the exact spots the AI was looking at when it made its decision. Suddenly, the AI isn't a mysterious black box anymore. It becomes a tool we can actually understand and trust.
And here's the proof, right here. On the one side, you've got the patient's original scan. But on the other, wow, you see the same image, but with these bright spots lighting up. That's the AI's focus. It's literally highlighting the tiny microaneurysms, the little hemorrhages, the real clinical signs a doctor would look for. We're not just being told this is severe, we're being shown why. It's visual proof.
And you know, this really brings it all home. All that code we wrote, all that training, that gives us the what. It tells us the diagnosis. But a technique like this, like GradCam, that gives us the why. And in medicine, if you want doctors and patients to actually trust an AI, you have to have both. No question about it. So, there you have it. We went all the way from a completely blank page to a fully trained, rigorously tested, and most importantly, an understandable AI that can help diagnose disease. Which leaves us with one big question to chew on, right? As this kind of technology gets better and better, what does that perfect partnership look like? How do we combine the raw analytical power of an AI with the wisdom, the empathy, the essential human touch of a doctor? Because that's the future that we're all building, starting right now.